Okay, so now we've learned a lot, and let's put this together to one big project. And just to, sum up what we will use here and what we've learned so far is we already knew the fit function. We know that point and near point can read out attributes. That can include position. And min-pos can be an alternative to find the closest position on the surface. Then we have distance to have the distance between two vectors, two positions. And then we have lerp to blend between two, states or values. Doesn't matter really. It can be attributes, can be positions, can be whatever. And if you combine all this, then you can actually build something like this. And I call this a magnetic field effect or something like that. So we use an object to deform another object based on the distance to it. Now this can also be a little bit of a homework. So this is why I wanted to show you the effect before we actually go into building this together. Because maybe if you want, you could try to build this yourself before we look at the code. Okay, let's do this. So we start from scratch with a completely new sphere that I want to have as polygons so that we have enough geometry to work with. Don't be afraid, as you've seen, can be pretty fast, the whole thing. And then, because it's the easiest, we take a second sphere as our controller. Let's make this smaller as well. And let's go. So we go through this one by one. What we want to do is we want to control these points here based on the distance to the control sphere. And we want to change their position. And what are those positions supposed to do? They should move towards this magnet. So this already gives us a couple of indicators. And one thing I always keep saying to my students is start with what you know. Do not start with what you don't know. And this is actually a super helpful sentence that I remembered for my whole career, because very often you don't know what to do. That's the case for everyone, no matter how much experience they have. But a good way of solving this is starting with what you are sure that you have to do. And very often from that, the things that you don't know yet will materialize themselves. So it's a trick that I would really recommend. Don't sit scared in front of an empty sheet of paper. Start with the part that you're sure about, and the rest will come automatically from that. And this is what we're doing right now. We start with what we understand first. So first of all, we wanted to change the position, right? And the position was supposed to move towards what? Oh yes, the closest position on the surface of the magnet. So let's call this P magnet maybe. It's longer, but maybe easier to read then. And where do we get this from? Well, of course, from the min-pos. I say of course, but this is actually a decision. Because the min-pos would read out the closest position on the surface of the sphere. I think this is a good idea when we later change this to maybe a different geometry, which is more complex. But theoretically, you could also say, well, I will always use a sphere and I don't care about the surface, I care about the center point. And in this case, I read out, well, from the only point that exists from the second input, the position, and the only point that exists will always be 0. So this is totally fine. This is also an alternative. Let's quickly check if that actually works. Well, actually, let's do it this way, even though it's a bit crazy, but theoretically, this should mean that all the points will end up in the center of the second sphere. And let's see, yes, that has worked actually. So let's come back to the other option, min-pos. And this should move all my points to the surface of the sphere, or the closest point on the surface, and this also works. So both approaches are fine depending on what you want. You decide yourself. And as you can see here, what I often do is I do not write down 30 lines of code and then hope for the best. That's not how you should work. Always start line by line. Okay, does that work? Moving on. Does that work? Moving on. Okay, so now we have this position where we want to go to. But as we've seen before, not all the points will reach that, but only the ones that are close to it. So it's up to you how you want to start with this, but I think I can start with a distance first. So let's calculate the distance, and I put this into my dist internal variable. Again, the name doesn't matter. We could also call it dist magnet, something like this. So distance to magnet, and this would be the distance between my current position and the position magnet that we already found out. And this distance here, we could say, just as a first test, only if that is lower than a certain threshold. So if my dist magnet is smaller than Actually, I should call this magnet dist. I think that would make more sense. Something like that. If this is smaller than a threshold, let's call this max distance, then the point should jump there. I hope this makes sense. So now nothing happens because my max distance is currently 0. So let's increase that. And there we go. Basically, we have what we saw before. This is our ray node that we recreated. Okay, that's great. That's cool. So, but it's not even close to what we saw before because it, it just jumps there. It's not this soft kind of alternative, but it seems like we're in the right direction. What can we do? We could control somehow the strength of this, right? And the strength would probably be based on what? Well, distance, right? So let's say that it will not jump completely either to my surface or not, but it will always be somewhere in between depending how far we are away. So how can we do this? Well, we could do this with a lerp, and the lerp would be, a blend between two states. So what would we blend? Somewhere between my old position or current position and the new position I'm jumping to, which is P magnet. And for now, just, to test this, let's first create a parameter for this called blend. Actually, let's call this strength so we can use it later. And this allows us to, blend between two states. One would be exactly on the surface. 0 would be my original position. And somewhere in between is, of course, 0.5. I mean, yeah, it's not as smooth as we hoped, but it's at least we can control the strength now. You might already know what to do next. We just control this lerp not by some kind of parameter for all the points, but we actually control it by the distance. So, okay, cool. So we need a distance controller. So let's call this maybe normalized distance or something, because we know that it has to be between 0 and 1. And how do we bring the distance between 0 and 1? Well, with a fit range, of course. So the normalized distance is based on the magnet distance, but we want to somehow put it between 0 and 1. And we need a fit for that. And what do we want to base this fit on? Well, magnet dist, right? This is actually our distance that we want to rearrange. And let's say if it's 0 meters away, then something will happen. And if it's 2 meters away, something else will happen. And what will happen? Well, let's say if it's 0 meters away, then we will want to put this in here. So when it's super close, then it should actually have the same position as the sphere, which is P magnet. So this then should be 1. Okay, so if it's super close, the result should be 1. And that means, since it's normalized, that answers our next question. What happens when it's super far away? Then it will be 0, because that will mean later on that we use our original position. And there we go. Now we have filled our normalized distance fit range. So let's see what this does. It doesn't seem to work. Well, the reason is that I chose 0 and 2 meters. And 2 meters is this range. So I just made a bad decision. What is actually the maximum distance that I want to calculate here? Well, wait a minute, I already have a max distance that I control. So let's use this again, because this is the same logic. So what we have here, and now we should already see a first version of this. Oh, wow, this is actually, well, we're almost done. So what's going on here? So if the distance to my sphere, the magnet distance, is smaller than the max distance that we defined, then something will happen. And what will happen? It will take that range 0 to max distance and map it to 0 and 1, which means when it's 1, it takes the whole position, and if it's 0, it takes its original position. In other words, the closer it is to the sphere, the more it will move towards the sphere. That's the idea. Yeah, we're basically done. That's it. Cool. Now, the only thing is, it's not super buttery smooth. It looks a bit, you can see that here, the edge. It's kind of, because it's a linear interpolation, it instantly goes up. If you look at a linear curve, it goes from 0 directly straight up. And this is what we see here, this little bit of a dent, like a little dent. Wouldn't it be nicer to have more like a, like a rounded curve? Can we somehow build in a rounded curve in here? Well, what would be a rounded curve? A ramp. Oh yeah, right. So actually, what we could do, since our norm dist is already normalized, let's just run this again through a ramp. So through a different range definition, basically. So we create a ramp and we put this norm dist in. And now the funny thing is, since the ramp takes a normalized number as an input, it will also give a normalized number as an output, because a ramp always gives back something between 0 and 1. So this actually is all we need to extend this functionality to do the following. We now have a ramp, and the default ramp is basically not changing anything, because this is basically what we had before. If the norm distance was 0, then the result of norm distance is 0, surprise. If the norm distance was 1, then norm distance was 1. And if norm distance is 0.5, then norm distance is 0.5. In other words, if you put a ramp in here, the default linear ramp, then actually it does nothing. Only if you start changing it can you see the difference. And the best thing I would recommend here doing is, again, softening that curve. Maybe an S-curve is usually a good idea. So in the beginning it starts less aggressive, but then later on it becomes stronger, and this gives us this soft behavior here, so that the distortion at the beginning, when the distance is the highest, therefore our norm distance is 0, is not as strong. And basically the change is just a little bit, but the closer we go, the stronger is the behavior. And this is actually what gives us this nice soft feel to it, this almost organic feel to it. And this is why this kind of curve is actually pretty common in the CG world, because it creates a pretty organic behavior. Very few things in reality are linear. So if I make this even more extreme, I can make it even softer. You can almost, this is where the feeling comes in, where you have to make decisions on the behavior you want. But basically, this is it. And now we can control the, distribution of the change along the distance via this curve. We can change actually the distance. So how far away should it look from the magnet? And we can, even if we wanted, we still have our strength here that we don't use anymore. We can actually put this in as well, because what we could do is we could multiply the whole norm distance, so the actual controller, so to say, with this additional strength controller, if we wanted to. So that we basically on top have the function of dialing the overall magnet effect in and out if we want to. So then we can just dial the overall effect down a little bit, and then it's simply less aggressive, as you can see here. Those kind of things, just multipliers, can help you to have even more control over your behavior. You could even animate this on top. So I hope this was helpful. The first bigger example of building a more complex setup from scratch with all the tools we had. I hope you learned something and it was helpful. So yeah, thanks very much and see you later. Cheers.